Have you ever really stopped to think about how a simple push on a pedal can stop a 2-ton car? Or how a mechanic can lift an entire vehicle with what looks like a tiny little pump? I mean, it kind of feels like magic, but it's not. It's actually pure physics. So today, let's pull back the curtain and look at the brilliant principle that makes it all possible.
This right here, this is the central puzzle we're going to solve. It seems impossible, doesn't it? How can a small, totally manageable force suddenly get multiplied into something powerful enough to lift a car? Well, the answer is hiding in plain sight, in the liquids that power our world.
And this illustration from NASA just nails the core idea. Look at the left side. A small force pushes down, but it has to travel a long distance. Then, on the right, that same action translates into lifting a huge weight, but only over a short distance. This isn't a trick. It's a fundamental law of how fluids work. So what is this seemingly magical force? Let's get right into it and unveil the puzzle.
And the secret, the key that unlocks this whole mystery, comes from a 17th century French mathematician named Blaise Pascal. Let's reveal his core principle. So there it is, Pascal's law. Now, the most important words here are transmitted without loss. What does that really mean? Well, it means that when you apply pressure to a liquid that's trapped in a container, that pressure doesn't just stay in one spot. Nope, it spreads out instantly and equally to every single part of that liquid. It's like an invisible, system-wide message that says, hey everyone, increase the pressure by this much right now.
And this diagram shows that idea perfectly. Look at the gauges before anything happens. They read 1, 3, and 5, just because of the weight of the water above them. But then you add 5 units of pressure at the top, and what happens? Every single gauge jumps by exactly 5 units. It doesn't matter if it's at the top, middle, or bottom. The pressure is transmitted equally, everywhere. That's the key. Now, for this to work, there are a few rules of the game. First, the fluid can't be something you can easily squash, like air. It needs to be incompressible, which is why oil and water work so well. It also has to be in a closed, sealed container. You can't have any leaks. Basically, you're just setting the stage for Pascal's law to perform its magic. Okay, this next part is maybe the most important piece of the whole puzzle. To really get how this trick works, we have to understand the difference between pressure and force. And trust me, they are not the same thing. This distinction is everything. So here's the crucial point. Pascal's law says the pressure is the same everywhere in the fluid. It gets transmitted equally. But force? Force is just pressure multiplied by the area it's pushing on. So if you have a really big area, that same constant pressure is going to create a much, much bigger force. The pressure doesn't change, but the resulting force absolutely does. If you remember just one thing from this whole explainer, please make it this sentence. Pressure is transmitted, but force is multiplied. That's the mantra of hydraulics. It's the pressure that does the traveling, but it's the force that does the heavy lifting on the other side. So let's actually watch this unfold step by step. First, you apply a small, easy push, an input force, onto this little piston with its small surface area. Pretty simple, right? And bam! That small push creates pressure that instantly floods the entire system. You can see from these arrows, it pushes equally in every direction, on every single surface it can find. And here's the payoff. That very same pressure now starts pushing up on this much larger piston. And because the area is so much bigger, that pressure creates a massively multiplied upward force. And just like that, a small push has become a mighty lift. And this equation right here is the math behind the magic. It's actually super elegant. It just says that the ratio of forced area on the first piston is exactly the same as the ratio of forced area on the second. So if the second piston has an area that's, say, 10 times larger, you're going to get a force that's 10 times greater. It's an incredibly powerful relationship. Now, I know what you might be thinking. This all sounds a little too good to be true, doesn't it? It feels like we're just creating force out of thin air. But you know, physics has a very strict no free lunch rule, so it's time for a reality check. This is the question that should be popping into your head. If we can multiply force this easily, have we just found a loophole in the laws of physics? Have we broken the law of conservation of energy? Are we getting free energy? The answer, of course, is a resounding no. And here is the catch. We're not getting free energy, we are making a trade. And as this slide shows so well, we trade distance for force.
To lift that super heavy weight just 1 inch, we had to push the small piston down a full 10 inches.
See, in physics, work is defined as force times distance. So the small force you apply moves a long way, and the large force you get out moves just a short way. When you multiply them, the work you put in is basically equal to the work you get out. No energy is created, it's just transferred and transformed. Now, in the real world, you'll lose a tiny bit to friction, but the principle is solid. So let's just quickly bust some common myths to make sure we're all on the same page. First, the pressure is not higher in the larger piston. It is equal everywhere. That's the whole point. Second, hydraulic systems do not create energy. They just multiply force by trading it for distance. And third, force is not transmitted directly. Pressure is transmitted. Getting those distinctions right is everything.
Okay, so now that we've pulled back the curtain and demystified the science, let's look at where you can see this amazing trick in action all around you. Seriously, Pascal's law is the secret sauce behind so many technologies we just take for granted. Your car's brakes, they use it to turn a light tap from your foot into immense stopping power. The lifts at your local garage, the landing gear on an airplane, massive industrial presses, even something as simple as squeezing a tube of toothpaste. And just think about that for a second. When you squeeze the bottom of the tube, you're applying pressure to a confined fluid, the toothpaste. And that pressure is transmitted equally all the way through the tube, forcing the paste out of that tiny opening at the top. It is a perfect, simple demonstration you probably do every single day. So, the next time you see a backhoe digging a trench or see a car up on a lift at the mechanic shop, you'll know the secret. It's not magic, it's Pascal's law. That simple, elegant principle of transmitting pressure to multiply force. So now that you're in on the secret, where else are you going to see this principle at work?